All right, hello everyone. We were talking about this critically damped natural response of a parallel RLC circuit, and in this lecture, part of the lecture, we're going to do the circuit problem very quickly. Again, you can use this table to get all the equations, or you can use this stepwise process again to solve any of the damped response for a parallel RLC circuit in case of a natural response, right? Which really comes down to finding the values of alpha and omega naught, figuring out which response it is, and if it is critically damped, then using this equation. And in order to use this equation, you have to find out the values of d1 and d2, and you can use these two equations to find the values of d1 and d2. Okay, so we're going to do an example problem today. Okay. Again, here's our beautiful circuits that we have been looking at while solving responses as well. So let me quickly go ahead with the solution. Again, in the step number one, we always find the initial conditions, and in this particular case, we are provided with the initial conditions. So one last step to do. Okay, so you had initial conditions given. Initial voltage is 0, and the initial inductor current is minus 12.25 milliamperes, and this is a capacitor initial voltage, V naught, right? And again, we are solving. Okay, so the first part is in this problem, and this is kind of an interesting thing. I should have maybe started with that. The first part over here is it is asking to solve the circuit such that you can generate a critically damped response, right? And it is asking you to pick a value of R. Okay. So interestingly, if you have an inductor and a capacitor, let's say the energy stored, it's a natural response. How well it is going to, I think I may have made this point in the past when we were discussing about the oscillation behavior, oscillatory behavior of the underdamped response. That depending on how you pick the value of the resistor, you can practically set up how omega naught and omega is going to look like, right? And this question is asking you to pick a value of the resistor such that your response, voltage response, will be critically damped. Okay, so how can we do that? Right, for a critically damped response, I need to make sure that my omega naught is equals to alpha, or my omega naught squared becomes equals to alpha squared, right? If you remember from the past example problem, we did this thing where we had 1 over 8 Henry and we have 125 nanofarads, and omega naught comes out to be 10 to the 6 radian square plus second square, right? So I need to make this equals to alpha, right? So I can do 10 to the 6, 1 over 2 times RC, and I can use that to find the value of R. Okay, sorry. R equals 1 over 2 times 10 to the 6 times 125 nanofarads. So the value of the R will come out to be 4,000 ohms. Okay, so again, in the first part, what we did was we are kind of designing a circuit in a way that we are making sure that we're going to generate a critically damped response. And in order to do that, we have to make sure that our omega naught and alpha squared will come out to be, omega will come out to be exactly the same as, omega naught comes out to be the same as alpha. And of course, by solving this, we can easily figure it out. And if we were to pick a resistance value, R equals 4,000 ohms, our alpha becomes equals to omega naught square. So great. Now let's solve for the part B, where we have to plot the voltage response, right? Let's say we don't know it's, in this case, we actually made it critically damped, but in case we don't know it is critically damped, the process is finding the value of alpha and omega naught and comparing, right? So we already have the value of omega naught, right, which is 10 to the 6. Let's find the value of alpha as well over here, which we made it. So our value of the alpha, 1 over 2 RC, should also come out to be equals to 10 to the 3. And again, omega naught square is 10. Sorry, tablet move down. Okay, so 10 to the 6 So omega naught is also 10 to the 3. Again, both of them are radians per second, right? So omega naught becomes equals to alpha. So it is critically damped. Why I ended up doing this exercise? Because let's say you don't know whether it is critically damped. In this case, we made it, but in case you don't know, you have to do this exercise where you find an alpha and omega naught and compare the two values. Right. Again, the unit for both of them is radian per second, both for alpha and omega naught. Let me write the units just to make it a point that writing units is important, right? Okay. So if this is true, if this is critically damped, and what was the voltage equation for the critically damped, right? We know that it was d1 t e raised to power minus alpha t plus d2 e raised to power minus alpha t. And we already know the value of alpha, which is 1000. Let's find the value of d1 and d2. And if you remember, we kind of solved for that. The value of the d2 was the initial condition of the capacitor, or the initial capacitor voltage. In this case, it is 0 volts, so nice, d2 is out. In order to find the value of the d1, the other equation that we had was d1 minus alpha times d2 equals 1 over c times minus v naught over r minus I naught. So d2 becomes 0, so this term became 0. So we are left with d1 equals 1 over c 125 10 to the minus 9 minus v naught 0 over r minus I naught minus 12.25 milliamperes. Okay, so this is going to make it plus. And if we were to solve this thing, we're going to get a value of d1 to be equals to 98,000 volts per second, right? If you remember, the constant A1 constant was coming out to be volts and A2 was coming out to be volts. And the constant B1 and B2 were coming out to be volts, and D2 is coming out to be volts. The units for the D1 came out to be volts per second, and this per second is because you have a T here, right? So make sure that you understand the units where they're coming from as well. Anyhow, so this is D1 and this is D2, and so we are cool. Let's just write down the equation and we are done, right? So your value of the VT was D1 times T e raised to power minus alpha T plus D2 e raised to power minus alpha T, right? Again, D1 the value of the D1 was 98,000 volts per second. The value of the D2 is 0, and value of the alpha is 1000 radian per second, or 10 to the 3 power 3 radian per second. So you can put all of these values in V of t to get this. V of t comes out to be equals to D1 98,000 times t e raised to power minus alpha minus 1000 t volts. And again, this is true for greater or equals to 0. And here's the equation of the critically damped voltage response that you should get for the circuit. And the BPAD asks you to solve this for 0 to 7 millisecond, and this is how it looks like, right? In a critically damped response, again, you get this kind of an increasing peak, and then it kind of decays down all the way over here to a steady state. Okay, so with that, this is the solution to the final critically damped response and the end of this part of our lecture as well. So the point that I want to make at the end of this lecture is, by this we kind of figured out that if we have a parallel RLC circuit, we did a natural and in case of a natural response, parallel RLC circuit and a natural response, if you which was the circuit, if you were to make write down its equations, it is going to come out to be a second order differential equation, and then you can assume its kind of response to be an exponent based response. We ended up deriving this characteristic equation, its roots, right? So this is really the summary of it. I think that you may need to solve any of these three responses in a parallel RLC circuit and the natural response, right? You should know how to find the initial conditions, literally then finding the alpha and omega naught value, comparing these two things to figure out which response it is, and depending on whichever the response it is, we derive different equations, right? So again, this one is for the over damped response, this one is for the under damped response, and this one is for the critically damped response. And then whichever the variables are here, you need to put down to figure it out, right? In S1 and S2, in over damped response, these are your roots of the characteristic equation. In the under damped response, we have omega d. The formula is over here, and then B1 and B2. And in critically damped response, we have just D1 and D2. And those equations are over here. And again, all these three equations were found by solving for V naught 0 positive and dV of 0 positive by dt. Yeah, all three of them, this including these ones is true. So you can always practically I don't know why this is happening. Yeah, I was making tick marks. You can practically use these equations to solve for any of these response circuits. All right, so with that, thank you so much. And then in the next lecture, we're going to start with a step response of a parallel RLC circuit. And then we're going to move to the natural and the step responses of a series RLC circuit. But we're going to be much more quicker moving forward with the rest of the derivations and example problems. All right, with that, thank you so much. Have a great rest of the day. Thank you. Bye-bye.